This video will show you how to define material properties using Patran 2010. I've now opened a blank database in Patran and I'm ready to define my material properties. I'll select the Properties tab and notice on the left that I can create an isotropic, orthotropic, anisotropic, fluid, or composite material. In this case, I'm going to create just a simple isotropic material. Clicking on isotropic sets the action, object, and method to create, isotropic, and manual input. I'll enter a name for this material, in this case aluminum. Then I'll click on Input Properties to define my material properties for the aluminum. I'll enter an elastic modulus of 10 times 10 to the 6th and a Poisson's ratio of 0.3. Now, this is enough information for a linear elastic material to be defined. Density is optional and is only required if you need mass properties in your model. I'll go ahead and enter it just in case. Also note that I have the option of entering a thermal expansion coefficient or reference temperature if these were required for the material in my model. Now I'll go ahead and click OK and apply, and I can see that aluminum shows up under my existing materials. So I've defined this material. Now I could go on and define additional materials to be used for other portions of my model, or I could apply this material to part of my model using element properties. Defining materials and applying them to your model is really a two-step process in Patran. We've done the first step here where we define the material properties, and the next step we'll show you later where using element properties you apply a certain material to a certain portion of your model. Next, I'd like to show how to create a more complicated material. In this case, I'll create a 2D orthotropic material. My action, object, and method are create, 2D orthotropic, and manual input. I'll enter a material name, in this case graphite tape. I'll click Input Properties, and now notice that I have more values available to enter. I have an elastic modulus in two different directions, a Poisson's ratio, and three different shear modulus values. In this case, they'll all be the same, but note that they could be different based on the material that you're using. I also could define density, but in this case, since I don't need it, I won't. I can then click OK and apply, and now I've defined the linear elastic constitutive model for my graphite tape. But I want to go further and define a failure constitutive model. So I clicked Input Properties, I'll change the constitutive model to failure. My failure limits will be stresses, and I'll use Hill composite failure theory. Now I can enter tension stress limits, and note that I can enter different values for each direction, just like I had different modulus values. I can also enter compression stress limits, and then shear stress limit and bonding stress limit. Once I have entered these values that I want, I can then click OK and apply. And now I've defined an additional constitutive model providing more information defining my graphite tape material. If I click on Change Material Status, I can see that this material now has two active constitutive models, my linear elastic properties that I defined first, and the failure properties that I just entered. By clicking on these here, I can choose to make certain constitutive models either active or inactive. In this case, I want them both to be active. My next step in defining my material will be to go ahead and define my composite laminate that will use my graphite tape material. So under Composite, I can select Laminate, and this opens the laminated composite form and sets my action, object, and method to create composite laminate. I can enter a name for this new laminate that I'll create, and I'll call it 8-ply symmetric. Because as we'll see, I'll define a symmetric layup for my composite. I can click on the existing materials that I want to use, and each time I click on this, it adds a row or another layer to my laminate. In this case, I want 8 layers. So I've defined this graphite tape as my material for all 8 layers. I can also define my thickness. In this case, I'll use 0.0054 for all 8 layers. And now I can define the orientation of each layer in the laminate. So I'm defining my layup right here. I'll start with a 0-degree rotation, then do a 45-degree, then a negative 45-degree, then 2 layers at 90 degrees. And then because this is a symmetric layup, we'll have a negative 45-degree, and then a 45-degree, before having the final layer be 0. So now I've defined my material, thickness, and orientation for each of the 8 layers in my laminate. I can then click Apply and see that I've created an 8-ply symmetric composite. This material is now available for me to use if I were defining element properties for portions of my model. So if I am in the element properties form and I go to select my existing materials, I can see that I now have 3 different materials to choose from. The symmetric laminate, my simple isotropic aluminum that I defined, or my graphite tape, 2D orthotropic material that I defined. So these are all of the materials that are defined in my database. Now notice that in this database I started with a blank database with no geometry or finite element model. I can define my materials at any point in the process of modeling in Patran. So I could take advantage of this if there's materials that I use commonly and define them first, and then save that database and use it as a template or starting point for all of my future analyses, and then when I get to the point where I need those material properties, they'll already be defined in my Patran database.